Part A in question 20 wants us to explain what it means when we say that this isomer of methylcinnamaldehyde is the E isomer. Kahn, Ingold, Prelog are just the names of the people who invented the EZ naming system, so it's basically saying explain how EZ works. So remember, it's based on priority of groups, and you need to use that word in explaining your answer. So for each of the carbons of the double bond, you prioritize the two things that are attached to it. So remember, if we just write these as carbons, we can put on the hydrogen that's there. So for this carbon, the way we prioritize is we look at the atomic numbers. It's not based on MR, which is a common misconception. Priority is based on the atomic numbers of the atoms attached. And you can see in this case, hydrogen has atomic number 1, carbon has atomic number 6, so carbon wins, and it's the priority. So it means this is the priority group on that side. For this carbon, you can see it's more complicated because it has carbon there and also carbon there, so neither of those wins. So what you then do is you say, well, what about the next set of atoms 2 bonds away from this carbon? And here we have an O and an H. Here we have H, H and H. And we just see, is there, as soon as you have a difference in that list, who wins in terms of priorities. So we have a 6 and a 1, a 1 and a 1 and a 1, so that one wins. Okay, so that has the priority, not because that group has a bigger MR, but because that oxygen has a bigger atomic number than any of these hydrogens here, and that's what gives it the priority. So this, therefore, is the priority group on this side. And what that means is that you can then have this imaginary line running down through the double bond like that, and you can see that the priority groups are on the opposite sides of that line, and that's what defines it as the E isomer. So to get the marks, actually all you had to do was to say that the priority groups are on opposite sides of the line, but you had to identify which those priority groups were. So the phenyl group there and the aldehyde group there, or you could draw rings around them or just put stars there like I've done, but somehow it had to be clear which were the priority groups. And so always be aware of that kind of thing in your answers. When it's asking about a specific example, don't just make a general statement. Explain how it relates to that particular example. And for future reference, make sure you remember how priority rules work, that they're based on atomic numbers, not the MR of the whole group. Okay, so now we have some questions about qualitative tests. So first of all, it wants a test which will confirm that both these compounds contain an unsaturated carbon chain. That means an alkene group, which obviously they both do. And the way you do that is you just add aqueous bromine. You can say in the dark, just to emphasize that we're not looking for a UV triggered radical reaction here. So add aqueous bromine in the dark, and both of them will decolorize. So that's the test, so you need to explain what you do. Add aqueous bromine. You probably don't need to say in the dark, but it's quite a good idea just to make the point that you're distinguishing it from saturated chains which would react with UV present. And then both would decolorize the bromine. So that's a good word. Not discolor though. Discolor just means the colour changes. So decolorize the bromine, or you can give the colour change, which is orange is the colour of bromine, to colourless. Don't say clear. You might get away with clear, but they might argue that it could still have a colour, and if you could still see through it, it would be clear as well. So colourless is the word to use. So that's the first one. And then it wants a test that will confirm they both contain an aldehyde group. So that doesn't just mean any old reactions that aldehydes would do. So you could, some of you may have thought of using dichromate, which would indeed react with the aldehyde group in both cases, oxidize it to a carboxylic acid, and you could look for the orange to green colour change. But the trouble is, primary and secondary alcohols do that as well, so that's not a specific test for aldehydes, nor could you use 2,4-DNP, because that would react with ketones as well. The one that's specific for aldehydes is warming with Tollens reagent. Okay, so Tollens reagent is the key for that one. And if you have aldehyde groups there, and only if you have aldehyde groups, you get a silver mirror formed by aldehydes. So that's that one. Okay, part 3. The general test for aldehydes and ketones is to add 2,4-DNPH. You can write out the full name if you want, 2,4-dinitrophenylhydrazine, but the abbreviation is fine. And you get an orange or yellow precipitate if an aldehyde or ketone is present. Not other kinds of groups with carbonyl compounds, so carboxylic acids, acyl chlorides, anhydrides, amides, they don't do this. It's aldehydes and ketones only. So that's the test it wants. First of all. And then it says, what could you do with the product of that test? In other words, with the orange or yellow precipitate, to work out which of these compounds would be which, because obviously they would both react. And this is a specific method you have to have learnt. So this isn't about just coming up with some crazy and wonderful idea. It's about just knowing the traditional way of doing that. And so what you do is that you can recrystallize the precipitate to purify it, and then you collect, wash and dry the crystals, and then the crucial thing is that you measure their melting point. So the purification is important here, because remember, impure substances, the melting point gets depressed, so it's important that you have the pure substance, and then you measure the melting point and you compare with a database. So you just look up the melting point on a database to identify the original aldehyde or ketone. And that's a method which is incredibly old-fashioned, but it's on the syllabus, and you can see from the exam it's one they expect you to know about, so make sure you learn that trick. In part C we have to complete this scheme, starting from cinnamaldehyde here. So just this reaction first of all is an easy one. NABH4, you should know, is the specific reducing agent for aldehydes and ketones, so it's going to leave the benzene ring alone, it's going to leave the alkene alone. You have to stop and think about those, but no, they're not going to react, but the aldehyde group will be reduced to a primary alcohol. So we've got the benzene ring is the same, the ketone group is the same, and you've just got to make sure you get the number of carbons right. So you've got carbon and then OH, so you're going to get that. Make sure you don't leave that carbon out, because that would be easily done there. So that's that product. Now this one, we've got to make this product from cinnamaldehyde, and you hopefully recognise that combination of a nitrile group and an alcohol group as the hydroxynitrile that you get from an aldehyde or ketone when it reacts with a cyanide, so potassium cyanide or sodium cyanide. In the presence of aqueous acid, you must have the aqueous acid there. And if you've learnt that reaction and learnt the mechanism, you can see why the aqueous acid has to be there. So make sure you learn the full condition, not just the KCN. So that combination will give you that. You could specify an acid, HCl or H2SO4, but make sure you get the aqueous in there, because that's important. Okay, so that's that product. And then there are two things that we can do with that. So if we do the bottom one first of all, aqueous acid does nothing to a benzene ring, does nothing to an alkene group, does nothing to a secondary alcohol. So all of those are going to be unaffected. It's the nitrile group, and again it's a reaction you just need to know, which is that nitriles can be hydrolyzed to a carboxylic acid when you treat them with aqueous acid. So if you've learnt your reactions, that was an easy question. If not, no chance. That's the nature of organic chemistry. You really have to learn it. So all of that stuff is unaffected, so you just copy it out, but the CN group just becomes COOH. Okay, so that's nitrile hydrolysis, that reaction. Now this one, the thing to do is to take heed of that big hint. Excess again usually means that more than one group reacts. And hydrogen and nickel adds hydrogen atoms across a pi bond, so you can do it here to the alkene group, but also here, because remember, a nitrile group is actually that. So you can add hydrogen across the nitrile group as well. So it will do both of those things. And so what you end up with is the benzene ring is unaffected. You can hydrogenate benzene, but it doesn't happen very easily, so you would normally assume that would be left alone under those conditions. So the benzene ring is still there. This alkene group, however, will become an alkane, and the nitrile group will become CH2NH2, which, if you draw it as a skeletal formula, makes it like that. Okay, so again, if you knew your nitrile chemistry, then those two were easy. If you didn't, no chance. Do the revision on those reactions. It's the key more than anything else to success in this paper. Next bit wants us to figure out what's going on in this reaction of the compound with iodine monochloride. So you may not have seen this before, but the thing to do is to recognise, well, it's just like a halogen. Instead of having two bromines or two chlorines, you've got two different halogens. But it's going to react in the same kind of way as Br2 or Cl2 would do. So you look at the functional groups and you think, will it react with the benzene ring? Well, no, because that would need a halogen carrier, which you haven't got. Will it react with the aldehyde? Well, no, that's not a reaction you know. But of course it does react with the alkene group. And so it's just going to be an electrophilic addition, just like you would get with Cl2 or Br2 with the alkene. Now it's at pains to tell you all about the electronegativities of iodine and chlorine, and of course that matters because it's going to make this molecule polar, so that's where we should start. That iodine monochloride has a polarity like this. Okay, so chlorine is delta minus because it's more electronegative than iodine. So we should state that so that they know that you've figured out that that's what the dipole is rather than guessed. Okay, so more electronegative than iodine. And so that makes a difference because it means that when it attacks the alkene group, it's the iodine end that's going to mount the attack, because remember, it's the attraction between the positive charge here and the pi electrons that gets the mechanism going. Okay, so let's write it out. So we've got, here's the compound, and here's the iodine monochloride, and we put on the dipole because that's crucial to the mechanism. And remember that all that happens is that a pair of electrons jumps out from the pi bond and is grabbed by that delta positively charged atom. So we have a curly arrow like that, coming specifically from the bond to the atom, and a second curly arrow like this, because as one pair of electrons comes in, another one gets booted out. And so that's our second curly arrow. And the consequence of that is that we're going to get a carbocation intermediate. And because of the asymmetry, we're going to get two possible outcomes. And I think it's worth drawing both of them. So that will give you a carbocation intermediate. And there are two possibilities, depending which end of the double bond, so which carbon makes the bond to the iodine, because you can see that when that pair of electrons is grabbed by the iodine, it could end up bonded either to that one or to that one. So if we draw them both, we can see what the issue here is going to be. So if the iodine bonds here to that carbon, then we're going to get this carbon will have lost out on the electron, so that will become positively charged, or we'll get the other one, which would have the iodine attached here, same carbon as the methyl group, and that will give us a positive charge there. And either way, we'll have Cl minus formed at the same time. Okay, and again we show the lone pair on the Cl minus that was created by breaking that pi bond and that sigma bond there and pushing that electron pair out onto the chlorine. So those are our two possible intermediates, and to complete the reaction, all that happens then is that that pair of electrons plugs into where the positive charge is, so either there or there. And that will give you two possible products. Either this one with the iodine attached to that carbon and the chlorine attached here, or the other way around. So the chlorine attached now there, and the iodine attached here. So those are our possible outcomes, and you have to decide which one will be the major product. And remember, you do that by comparing the carbocation intermediates. This one is tertiary, meaning that the carbon with the positive charge has three other carbons attached, whereas this one is secondary because that positively charged carbon has only two other carbons attached. And you have to remember that tertiary ones are more stable and therefore more easily formed than secondary ones, so that's going to be preferentially formed, and therefore that's going to be the major product. So that's what you just have to explain to finish it off, which is that this carbocation with the iodine attached there, is the more stable carbocation because it's secondary rather than tertiary. Sorry, tertiary rather than secondary. Okay, so you've got to spell that out. Don't just say it's the more stable one, because they'll want to know why. Because it's tertiary rather than secondary. And if it's more stable, it's formed more easily because carbocations are higher in energy than the reactants, so you need to find extra energy to reach them, and the higher they are, the more difficult it is to find that extra energy. So it's the more stable one, so it's formed more easily. And hence leads to the major product. Okay, so this is the kind of explanation you need. It's got to be very clear that you're talking about the stability of the carbocations, not the stability of the product. So this is the more stable carbocation, and therefore this is the major product. And that's it. You've sorted the whole thing out then. So there was quite a lot in that, And the only thing that made it difficult was having this rather than just CL2 or I2. But it's always just a small step from what you've memorized to what you've got to apply it to, just tweaking things ever so slightly. And so long as you registered which way around the dipole was going to go, the rest of it should hopefully have been fairly straightforward if you'd learnt your electrophilic addition.